Can we start? Okay. So welcome to our regular Monday seminar. It's a pleasure for me to welcome Matyáš, and he will give a talk on facility automation.
Thank you for the introduction. So I will be presenting joint work with Sergio, Aaron, and Tomáš. We will soon present it on ICAI. And I will start with the description of the problem. So in our world, everything is happening on a real line, and we want to build a facility. The facility can be of two types, type 1 and type 2. And then there are some agents which will use the facility. And each agent has interval in which the facility is useful for him. So if it is outside this interval, it is useless. If it is inside the interval, they can use it. And they also have a preference for the two types. So agent 1 prefers first facility with 0.2, the second facility with 0.8. So the utility of the agent is easy to measure. It is just his preference for the facility if it is inside this interval, otherwise it is 0. What we want to maximize is the total utility over all agents, the sum of their utilities. So if we know all the information which agents prefer what, then it is easy to find the optimal solution. An algorithm could simply check like every different position where we can place the facility, compute the total utility for each, and then take this. This would be trivial. So in this case, the optimal facility would be here, and it would be facility 2 with total utility of 1.4. But in our setting, we assume that the agents can lie about some information. So in this setting, we will assume that the positions of the agents, those are publicly known and they cannot lie about it, but they can lie about the preferences between the two facilities. So, and the agents want to maximize just their own utility, so they can use it to try to help themselves. So you can imagine if we have these three agents, then, in the original solution, the agent 3 is not very happy because he gets nothing. So, and he knows, we assume that all the agents know exactly how the mechanism works. So they can change the values that they report so that they get better outcome. So in this case, if the third agent reports that he has 0 preference for facility 1 and 1 preference for facility 2, then from the reported information, it looks like the optimum position to place the facility is here, and it would be with utility 1.6. But his actual utility is still 0.4 and 0.6. So the actual utility would be 1.2. So you can see that in the case where the agent lies, it's actually worse than when everybody was telling the truth. So this work is about how to deal with this. So are there any questions about the model so far?
So we are only placing one facility.
Just one facility, yes.
And we have to decide whether it's the first one or the second.
Yes, we decided. Yeah. So now our task will be to design the mechanism that places the facility. First, we want to get a good approximation ratio. That is the ratio over the optimal value if everybody was telling the truth, guaranteed to tell the truth, over what will be the actual placed utility after the facility is placed. And the second requirement is that this mechanism should be strategy proof. That means that no agent can benefit themselves from lying. They will have no incentive. They will not get a better utility if they lie. So formally, we can define these things formally. Of course, one thing that I didn't mention is that these preferences are technical probability vector. They are between, the values are between 0 and 1, and they sum up 1. And just to reiterate, the mechanism outputs the type and location, and the utility for the agent is its preference if it falls into this interval. And we optimize the sum of all the utilities. So we will consider several settings. As I said, the setting where all information is public, that's trivial. And then there are three remaining possibilities. The preferences and ranges can be either known, guaranteed to be true, or reported by the agent. So we consider all the three remaining cases. We also distinguish between deterministic and randomized mechanisms, and we also consider the case where we have more than two facilities. So for each of these settings, we try to determine an upper bound on the approximation ratio. So this is achieved by designing and proving that mechanism achieves this approximation ratio in the worst case. And we show some lower bounds. So the first one means that no mechanism can have better approximation ratio than 24/23. So this also shows that we cannot have a mechanism that always outputs optimum. So the first, actually the best mechanism that we have for the randomized settings is very simple. So one way to make sure that the agents cannot benefit from lying is to just ignore what they say. And the first mechanism does exactly that. So we take a look at all their intervals. We pick the point which is most popular among the agents. And then we choose the facility uniformly at random. And this is easy to prove that it is two approximation. In case of random facilities, we try to maximize the expected values of the outputs. And agents also want to maximize their expected utility. And in this case, it turns out that the expected total utility is simply the number of agents that prefer that position over 2. And also an upper bound on the optimum is just the number of agents that are in this pile. So this simple mechanism is to approximate. So on the other hand, we want to show some lower bounds. So first, I will start with the lower bound for the deterministic case. So the mechanism has to be deterministic, and we will show that the approximation ratio cannot be better than 4/3. So we will take a look at those two possible instances. This is the interval of some agents. These are their preferences. And we will basically look at all the possible choices the mechanism can make. And we will show that always in one of those two instances, it will not be a very good solution. So those two restrictions are that the approximation should be at least this good. And we have to upload the strategy proofness. So in particular, if we decide some solution on this instance looks like this agent is lying about their position. So the agent here cannot have better outcome than here. So in this setting, we assume that the preferences are known. They cannot lie about it, but they can lie about the positions. So first, we can think about where facility can be placed on this input to get a good approximation ratio of better than 4/3. There are only two choices. We can place it either here and pick type 1, which will give us utility 2, or we can put this symmetric other solution and facility 2, and we get again 2. Any other choice gives us utility 1 or worse. Okay, so suppose that some mechanism picks this as the solution. Then what the mechanism can do here? Well, again, it can pick either some solution that would be 1 or worse. That's already a bad approximation ratio. Or it can pick this solution. This will give us 3/2. But in particular, it cannot pick this solution with facility 1, so with the facility 2, because this agent would harm themselves by lying. So this means that in one of these, due to strategy proofness, we have to get a better result. So then we have the optimum 2, and the best we can do on the other instance is 3/2. And now we have 3/2, which is the approximation ratio of 4/3. So now we look at the randomized case. So this is too much detail, so I will focus just on the technique. we start out with some a bit more complicated instances. And again, the important part is that this agent, in this instance, looks like this agent 3 line. The agent 5 could be either a true reported preference or it could be agent 3 line. Similar here, agent I6 looks like it could be agent I4 line. So the idea from afar before, it was to consider all the outputs the mechanism can have on these instances all together, tied together with the strategy proofness, and show that in one of these instances it will be far from optimal. So in the deterministic case, we could consider all discrete cases, but here, because of randomization, we have some distribution over the outputs. So that cannot be, that means that there is like an infinite number of distributions that the mechanism can choose. And we will need to solve this analytically. So one way to imagine this is that the mechanism actually just outputs the distribution over the positions joined with the facility type. And then we could sample from this distribution, and it would be equivalent to just the mechanism doing something random. So we will reduce finding this lower bound to an optimization problem. So our decision variables are the terms that define the joint probability. So Q, I, J, K, that's the probability of choosing facility 1 on position J in instance K. So for a fixed K, this has to sum up to 1 and has to be non-negative. So these are the decision variables for the problem. The constraints are the natural ones by definition, such that it is positive. And the important one is the one that follows from strategy proofness. So again, let's say that agent U5 in instance 1, in instance 2, looks like a lying agent on instance 3 in instance 1. So this way we want to encode that their utility cannot increase in the instance where it looks like they are lying. Then the expected value of the utility, that's just a linear function in Q. The coefficients come from the inputs that we have, the facility and location preferences. And the expected total utility is still a linear function of this. And then what is the objective of this optimization problem? So this maximum, okay, so this term, that's the approximation ratio on instance 1, the optimum over its expected utility. Now we look at the worst case over all of these instances, and we minimize because we want to find out the smallest possible worst case. And we minimize over the Q. So if we analyze from afar what this is, so each of these is a polynomial. The optimum is fixed value, which we can pre-compute. So if we take maximum over the 3 polynomials, that's just a piecewise polynomial function, and we can compute this still analytically. And we can also find the minimum over these, the global minimum, also analytically. So that's what we do, because it would be a huge computation. We use Wolfram Alpha, and Wolfram Alpha can do all of these computations symbolically. So as long as you believe that the implementation in Wolfram is correct, then the provable minimum here is this 24 over 23. So one thing worth mentioning is that what you see here is also basically a linear program. What doesn't fit is just this minimum over maximum, but it can be rewritten as a linear program. The reason we didn't use a linear solver is so we do not have to deal with numerical resolution, numerical solutions. You can get like this analytical exact result. So I've talked about the setting with known preferences and reported ranges. For the other setting with known ranges and reported preferences, we use basically the same techniques, and I will skip over that. So another different topic that we explored in the paper is random dictatorship. That's a paradigm sometimes used in these kinds of settings, where we pick an agent at random and we let them decide the solution. So we were exploring this because it's such a known paradigm. And first, in general, this will not work in this case very well. You can imagine that if we have a lot of agents with disjoint intervals, then and we pick one of them, then they help just themselves, and the facility doesn't help anybody else. You could have a lot of disjoint agents and one pile of agents which could give you a better optimum, but the probability of these disjoint ones could be still arbitrarily high. So in general, we cannot get like a fixed constant approximation ratio with just this. So we'll restrict what we look into a bit. We'll look into the case where the ranges are known and the preferences are reported. And we will restrict this random dictatorship a bit so that we select the agent just from the pile with the highest number of agents. So that we know that at least the location that will be fixed by the mechanism, that will not be random, and it will be like what looks like best possible location. And then we select one agent randomly from that, and let him pick just the type of the facility. And the result we get is that the agent can still exploit this in a way that leads to worse global outcome. The first simple random mechanism was too approximate, and this random dictator is 16/7 approximate, which is like 2.3 or something like that. I will just go also quickly go through the technique that we used here. So again, this is a randomized mechanism. So we will analytically try to find the worst case for this mechanism. And first, let's assume that all the n agents prefer the same location, and then the rest is just some like more technical work. So first, you can see that the optimum is at most the number of agents, and then we will describe this pile of agents by smaller number of variables. We will have Ci as the fraction of agents that prefer facility I, and Qij, that is the average preference for facility J among agents that prefer Y. And this definition of variables is useful for us because it is enough to express the expected utility of this mechanism. So when we write out the expected value of the utility, we have this probability that facility 1 is picked, that's just proportional to the fraction of agents that prefer it. And the utility, part of the utility comes from C1 agents, and their preference is in Q, and the other part comes from C2. So in the end, when we write out the calculation, we end up with something that is a polynomial in C and Q. And that's nice for us because that's just like 6 variables. So in this case, we can show that the expected utility over n is bounded by the minimum of this polynomial. And again, in this case, we can find the minimum analytically. We again use Wolfram alpha for this. And what's nice also about is that the analytical solution tells us the values for these variables. So we use that back again to construct the worst case instance. So it tells us that what is worst for this mechanism is 1/4 of agents just want their facility and nothing else. And the other 3/4 are half and half. So based on that, we can construct an instance where this mechanism actually gets this 16/7 approximation ratio. We can put n-1 agents here with preference for 1. This will be the optimal placement, and we would get utility of n-1. And this one has the ratios and preferences as given by the optimization. And then if we take a look at the ratio of optimum and the expected total utility, we get something very close. And by increasing n, we can get arbitrarily close to the ratio that we proved. So we also considered the case of more than 2 facilities. The simple random facility mechanism still works and approximate. And we found out that this variant of random dictatorship gets a lot worse with more facilities. The approximation is m². That's asymptotically tight from both sides. We know we have like a family of instances where it ends up with this roughly m² approximate optimum. And that's basically all I wanted to say. For the next steps where we want to continue is we can extend the technique for the lower bound that we used. So I showed we had some like 2 instances and 3 instances. We could write a program that considers a much larger number of instances. We could use a linear solver for that and find a nicer way to prove that it is actually optimum with maybe some duality or something like this. So that's one direction that we would like to look into. And we are thinking about some ways where we could use this linear program to sample some space of the inputs, get some solution from the solver, and this would be like a template for a mechanism on this limited number of inputs, and we could somehow extrapolate for other ones. So these are ideas for future work. And of course, there's a lot more different variants and models to always consider. So this is everything from me. Thank you for your attention.
Okay, thank you for the talk. Now, questions and comments.
So you had the table with lower bounds and upper bounds, like 8. If it's not filled out, that's open, or it's unbounded?
Oh, that is open. That is open. We didn't look into that.
For the lower bound 34 or 23, so you consider some instances where you put some, I mean, there are some like quarters and this stuff, and you optimize something over that. So do you actually know that, like, do you know whether there is like a better construction for this? Like, you try to optimize over the construction to give you better result?
Not really. So what was kind of limiting us is that if we use like larger construction, then Wolfram Alpha has trouble with the calculation because it tries to solve all of the equations analytically. And
so what will happen if you, like, I don't know, like parameterize those 1 over 4, 3 over 4 with something else, and then you just forward it and then just minimize over some more variables?
That's a really good question. So I actually tried to set these 2 as a pre-variable. Actually, there is only one. The other is a complement.
Yes.
I tried to minimize over that. It turns out that you should have here something like 1 over square root of 2 or something like this. But at this point, Wolfram Alpha couldn't like solve this symbolically, because my guess is that because then you get inequalities with like square roots and stuff, this gets somehow a lot harder. So actually, this is probably the lower bound is definitely like higher than what we have here, but it's a bit more difficult to prove.
So you assume that some agents are lying, and you assume, if I understood correctly, that the lie can be arbitrary. They can say whatever they want.
Yeah.
Would it change a lot if you bound how much they can lie?
Yeah, that's a good question. I'm pretty sure it would change a lot. So like in all of these constructions, I assume that they can they have to change their output a lot. So it would definitely change the result. Yeah.
I think even the first example, if you, for example, just say you can report your position to only inside like some epsilon for your real position, the first example wouldn't work.
Yes, yes, that's true. Yeah.
I guess.
It would also limit how much they can like change the global utility or the perceived global utility. Yeah.
Okay. There's no other question.
Okay, so. Okay, so what about more languages?
Do you mean like
Everyone is a square.
yeah, that's also a good question. So actually, most of the results don't really use the fact that it's an interval. It can be just like, if it would be like a discrete set of positions, it would work the same. We somehow need to be able to compute these things, that what is like the most popular position and stuff like this. But as long as we can do that, so then we are fine. So it could be much more general than intervals. But we are presenting for people with practical interest, so you wanted to make it nicer for presentation.
Okay, so